Alright, so far we talked about the two risk measures, VAR and ES, their properties and the proofs of their properties. Now, what we have talked about so far is not going to be useful unless we can estimate the two risk measures. So I'm going to start talking about how we can estimate VAR. Right? Estimation is a crucial part of any statistics. So there are three parts to this estimation. The first one is the parametric estimation methods for VAR. So what I mean by this is that you assume that the losses, say losses of a company, follow a certain distribution, like for example the normal distribution, which has two parameters, or the log normal distribution, which has two parameters, or the Gumbel distribution, which has two parameters, and so on. And the second section is non-parametric estimation methods. So what I mean by this is that you assume that the losses do not follow any particular distribution. So you try to find ways to estimate VAR without assuming that the data follows any specific distribution. And C is semi-parametric estimation methods, and this is a combination of the two. So there are certain parts of this method which are parametric, and certain parts of this method which are non-parametric. Right? So now in this video I will talk about parametric estimation methods. So I'm going to talk about part A in this video, which is about parametric estimation methods for VAR. Okay. Okay. All right. Now, before I start talking about parametric estimation methods, I need to briefly remind you of some of the stuff you learned in your year 2. That is, if you did your undergraduate degree here in Manchester, I need to remind you of something. So, first of all, suppose this is kind of a reminder of what you did in year 2. Suppose theta hat is an estimator of theta. So theta is a population parameter. Theta hat is an estimator based size n. All right. The first thing you need to remember is the following. Then theta hat is unbiased. This is the crucial word, unbiased, if the bias of theta hat, which is defined to be the expectation of theta hat, minus theta is equal to 0. So the second thing you need to remember is that theta hat is asymptotically unbiased. So I'll put this in a box. These are keywords you need to remember from year 2. Asymptotically unbiased if the following is true, that is, the limit as n approaches infinity of the bias of theta hat is 0. And the third thing you need to remember is the following, that is, theta hat is consistent if the following is true. The limit of the MSC, I will define what that is. I will define this in a minute. As n approaches infinity is 0, right? Where MSC is defined as follows. It's defined as the expectation of theta hat minus theta squared, right? And MSC stands for mean squared error. Okay, this is the meaning. This is the abbreviation MSC, right? So these are three things you need to remember from. So let me put this in a box so that you know what I'm talking about. I mean, these are stuff you did in year 2. If you don't remember or you should feel you did not do it, you may want to check up the material. So these are from the course that you took in year 2, which is called Math 20812, and the name of the course was Statistical Methods. Right, and so you ought to have done all this in this course. It was taught by Professor Streimer, Corbinian Streimer. And I think he has a website containing the material for this course, and so if you don't remember any of this stuff, you may want to look up the website. And I used to teach this course years ago, and I still have a website for this course, which is as follows. This is my material for in the following website, which is, I'll write it down, https not IT, let me erase this. Then Minerva, MINEERVA .it.Manchester .ac.uk, then this slash here, and then the tilde sign, then my first name, which is SARALEES, then the slash, then MATH, all in capital, then 20802.ac.uk. HTML. So this website here contains the material for statistical methods during the time I taught the course, right? So you may want to look up this website too, right? Okay, so that's just kind of a reminder. Now let me get on with the parametric estimation methods for VAR. So the first method I'm going to talk about is the following. So method number 1 is based on the normal distribution. So I shall suppose that the losses, say x1 to xn, are IID from a normal distribution with parameters mu and sigma squared, right? Okay, so now we know from the previous videos I did for you that the formula for VAR is given by this. Right? Obviously there are two parameters which are unknown, mu and sigma, so we need to estimate them. All right. The first. All right. This is where the second year course comes in. The MLEs, the maximum likelihood estimators of mu and sigma, are as follows. Mu, this is, you should remember this from year 2, that the estimator for mu is simply the sample mean, right? And the estimator for sigma hat, sigma is simply equal to this. All right, so these are the, if you don't remember, just please go to the website I just showed you. So let me put this in a box, right? So this is come from Math 20802, right? Okay, so hence, so these are the MLEs for mu and sigma. Hence, the MLE of VAR is simply the following. So you just replace, in this formula here, you replace mu by mu hat and sigma by sigma hat. Right? So this is the MLE for VAR. Right? Okay, now it can be shown, I'm not going to show it, but I invite you to do this. can be shown that the estimator given by this is asymptotically unbiased and consistent. In the previous slide, I showed you what those two means, that what asymptotically unbiased means and what consistent means, right? So I would like you to try to prove that this is in fact asymptotically unbiased and is also consistent when you have time. Okay. Right. The next thing, the second method, the second parametric method I would like to talk about is the following. Number 2. Sorry, the ink is keep coming. Sorry. This method is based on the uniform distribution method. Based on the uniform distribution. Okay. Now suppose suppose that you have a random sample IID from a uniform distribution with parameters A and B, right? We know that from the previous videos that the var is equal to this. And you should remember from year 2 the MLEs of A and B are as follows. The MLE for A is the minimum of the data, and the MLE for B is the maximum of the data. So these are stuff you should remember. These are stuff you should remember from year 2, right? All right, hence the MLE for var is given by this. So you just replace A by A hat and B by B hat. Now once again it can be shown that this estimator is asymptotically unbiased and consistent. So whenever you have time, please try to show that this is asymptotically unbiased and consistent using the definitions I gave you a few slides ago, right? All right, the next method I'm going to talk about is the exponential distribution method. So this is number 3. So I'm going to suppose that the losses, say x1 to xn, right, are IID, from an exponential distribution with parameter lambda. Now we know from the previous videos that the expression for var is given by this minus 1 over lambda times log of 1 minus p. And you should know from the year 2 course statistical methods, the MLE of lambda is the following. Right? So you should know this from, you should know this from year 2, right? Now if you sub this into this, you will get the following. You will get right. This is the maximum likelihood estimator for var. Now it can be shown that this estimator is unbiased and consistent. So this is little different from the 2 previous methods. In the 2 previous methods, the estimator was asymptotically unbiased. But here, the estimator is actually unbiased and consistent. And it's not difficult to show that. And once again, when you have time, please try to show that. Okay, now the next method, number 4, is the power function method. So I'm going to suppose that the losses x1 to xn IID with CDF equal to this, where x is between 0 and 1. Now, this is something we haven't covered in the previous slide, so let me show you how to find the the var for this. So in order to find the var, we just simply need to set fx equal to p and solve for x in terms of p. So this implies that x to the power a is equal to p, and this implies that x equal to p raised to 1 over a. So hence the var for this distribution is equal to this. Now we need to estimate a. I don't know whether you covered this distribution in the year 2 course. So let me show you briefly how to derive the MLE for a. So the first thing you must do is to write down the likelihood function. The likelihood function, remember, is the product of the density function, but what you're given is the CDF. So you need to differentiate the CDF with respect to x to get this. This is the density of this, right? Now, if you simplify this, this becomes this, right? Hence the log likelihood. So this is the likelihood function. The log likelihood function is, you take the log of it, so it becomes this. All right, and the next step is to take the derivative with respect to a. So the derivative with respect to a is going to be this. And you set this to 0 and solve for a. And if you do that, you get a hat, okay, equal to minus n divided by the sum of log of xi. Now, to make sure that this is a MLE, right, to make sure that this solution is a MLE, we need to take the second order derivative. So the second order derivative is as follows. Right, which is minus n over a squared, which is a negative number indeed. So hence what we have here is a maximum likelihood estimator. So So that's what I'm going to write over here. Hence, a hat given by this is an MLE of A, right? And hence the MLE for var is equal to this. Right? All right, so that completes the power function distribution method. Okay. Number 5 is the known as the variance-covariance method. Variance-covariance method. Okay. All right. Now, this is slightly different from the previous methods because this method concerns a portfolio. Now, suppose suppose a portfolio has M investments, right? And let Xi denote the loss on investment I, right? And let Wi denote the weight on investment I, right? Okay, because certain investments are more important, may be more important than other investments. So this gives a weight, right? Then the total portfolio loss can be written as this. All right. Okay. Now suppose that the loss on investment I has a normal distribution with parameters mu I, the mean, and sigma I squared, the variance, and are independent. then it can be shown from what you learned in year 2, right, can be shown that, I mean, this, you must know this, that if you have independent normal random variables, then their linear combination is also a normal random variable. So this has a normal distribution with the mean parameter equal to this, and the variance parameter equal to this. All right. Okay. Now let's see how we can find the value at risk for this variable x, which represents the total portfolio loss. So the first thing I'm going to do, as I said in the previous method, I'm going to set the CDF of x equal to p, right, and then solve for x in terms of p. Now, because x has this distribution, it means that the CDF of x is phi Okay. All right. Now, if you solve this equation for x, right, you will get the following. All right, so this is the expression for x in terms of p. Hence, the formula for var of x at p is equal to what I have just written down. Okay, so okay, so this is the formula for var under the variance-covariance method. Okay, now let's see how we can estimate this. Right. So here we are again. So suppose you have the following data. Right, suppose you have the following data. So suppose the data on the first investment, that's the losses on the first investment, are these, right, on x1. And suppose the data on the losses on the second investment are these, right, and so on until you have m investments. So these are the data on the loss on the mth investment. Then it can be shown, once again, once again, you need to refer to, I need to refer to the second year course. The MLEs of mu I and sigma I squared are as follows. So the MLE for mu I will be this. All right, and the MLE for sigma I squared will be this. All right, so these are stuff you should want to know where these come from. This is from the stuff you learned in year 2, right? So this is from Math 20802. Okay. All right, hence, so using these two, sorry, there should be a hat here. Hence, the MLE of var under the variance-covariance method is as follows. Right. So this is the MLE for var. All right. Okay. So that's method number 5. The final method, number 6, is the following: is the Weibull distribution method. Okay, guys. All right. So I'm going to suppose that the losses x1 to xn are IID with the CDF equal to the CDF of the Weibull distribution, which is given by this. Okay, now the first thing we must work out is the expression for var. So I'm going to set the CDF equal to P and solve for x in terms of P. So okay, so this implies that right, and this implies right, and hence x is equal to theta times this, and hence var, the expression for value at risk, is equal to theta times minus log of 1 minus p power 1 divided by beta. Right. Now it can be shown. We need to estimate, there are two parameters, theta and beta, right? It can be shown that the estimator for theta and the estimator for beta are the solutions of the following equations. This is the gamma function, which I talked about before. Right? Right. So theta hat and beta hat are the solutions. So you will need to solve these equations using a computer package, right? Where x bar is the sample mean, so simply 1 over n times the sum of the data, and s squared is the sample variance, which is, you might have seen this in year 1 course, which is 1 over n minus 1 times the sum of the squares of the deviations of the data from the sample mean. All right. I don't expect you to prove this, but I mean, if you can prove, that's great, right? Hence, an estimator for var is you just simply replace theta by theta hat and beta by beta hat. So you get the following: get var hat theta replaced by theta hat, and beta replaced by beta hat. All right, so this completes the sixth method, and this also completes the parametric estimation methods for value at risk. In the next video, I shall talk about non-parametric estimation methods for VAR.